Hi everyone, we are Notes Expanded. We would like to present our techniques used in the Pacman Tournament AI planning for autonomy University of Melbourne. This game is about building AI agents to eat as many foods as possible in other enemies' grid. There will be two sides of the team, the red team and the blue team. Agents will be enghosted in their respective grid, and whenever the agent leaves the grid, they will become Pacman, which can eat the enemy's food, but can be dead if eaten by enemy's ghosts. The winning condition is whenever the team can bring food to home until it is left to or none at all in the enemy's grid. So the normal strategies will having one offensive agent and one defensive agent. Nevertheless, we will explain our approach, which is first using the MCTS and second using the A-star search. We will explain about the MCTS approach. First, the selection. We first assign infinity to nodes that we are not visited yet to indicate that we should visit that node as long as it is not the terminal state. We then evaluate the UCT values using the reward we get when simulating plus UCB, then select whichever has the maximum value. We then expand the node when it is not visited. Then for each node, we will simulate for X time with XDEF. We then will get the reward, which will backpropagate to parent, and each expanded node will be assigned a reward value. We will be using these 5 rewards as guided for the agent, with being dead will get the biggest penalty. We also overcome a challenge by assigning penalty when agent facing dead end. The use of exploration versus exploitation and combination of rewards make the agent unpredictable and eventually can steal many of the opponent's food. But it is also a pitfall because sometimes we don't know why the agent acts in such a way. Other pitfalls is that the agent sometimes is too scared. Here we can see that it is actually safe to eat the foods. Instead, the agent just go back and forth. Due to these pitfalls, we will be focusing on A-star search instead.
I'm going to explain about our second approaches, which is using A-star. So during this presentation, it is assumed that the red is our agent while the blue is the enemy agent. A-star is an informed search problem algorithm which is based on heuristic value. It is quite easy to control the behavior of A-star by defining a goal that we want it to follow, such as searching for the food, home line, Pacman, and capsule. The formula can be seen, which is Fs equal to Gs plus Hs. The heuristic value in our cases are used to avoid ghosts, which can be seen in this GIF. To avoid them, we modify the value of H by increasing it so that when the enemy are nearby, our Pacman will avoid those actions. So this yellow line is the home line, which is going to be used as the goal. So what is the goal for the offensive agent? Well, the main loop of the offensive agent is to go to the home line and to check if there's an enemy in our bases. If the distance is 1, then eat the enemy. If not, goes to the enemy field. Once in the enemy field, the offensive agent will start searching for food while avoiding ghosts, where the normal threshold is 3 food before it goes back home. However, there are special cases. If the agent has eaten 2 food or more, then it will search for a capsule if it exists. After eating capsule, the agent will keep attacking until 30 steps, then go back home. If it doesn't exist, then it will check if there's no enemy nearby and the other parameter, which can be seen in the full chart. If it fulfills, it will change the threshold of eating food to 7 before it goes back home. This will be repeated until there are 2 food left in the enemy field. So what is the goal for the defensive agent? Well, our defensive agents are capable to attack during this condition. If it hasn't attacked at all on this round, then it will search for food for 150 steps, then goes back home. When the capsule is eaten, then the defensive agent will search for food for 20 steps, then go home. When the defensive agent is scared, then will search for food for 30 steps, then go home. Other than that, the defensive agent will mainly goes back and forth from the home line to the last eaten position. During those time, if it finds an enemy, then it will pursue them until they are eaten or go back home. So what is the main benefit of using A-star? So our agent is work best when there's path to goes home and it isn't blocked at a wall, but it can be seen here. And the agent can avoid ghosts on site, as seen in this illustration, or offensive agent choose to avoid enemy defensive agent instead of running towards it.
One of the challenges that we found from our approach was our offensive agent refused to go straight home even though it was right beside it. We solved this by using base distance and finding the shortest home line before defining it as a goal for our offensive agent. The second one was how to determine enemy position outside vision. We solved this by looking at the list of food and determine enemy position by comparing food on current and previous steps. And now I will explain the pitfalls of our agents. Our offensive agent sometimes got stuck because it's trying to avoid ghosts and take the shortest route to goal at the same time. And the second pitfall that we met was our agent eats food on dead ends because it does not prioritize food location on map. To avoid this in the future, we're planning to first prioritizing food to eat and path to take to prevent agents going to dead ends. And second one is making agent to do a U-turn after getting stuck in same position for a period of time. We acknowledge that MCTS has an upper hand in offensive agent by its unpredictable nature. We would like to improve our MCTS and combining it with defensive A-star to create better agents in the future.